Hi guys, so that's going to be my last video in the series Geometrical Optics. So we're going to cover reflection in a nutshell. So about about a mirror, a plane mirror. So we already covered that. The light will bounce off, kind of a bouncing ball. And this angle here is called the angle of incidence. This angle here is the angle of reflection. And you see they are the same. They have to be the same. And this is an imaginary line. We call that the normal line. It's perpendicular to the surface. So what you see in the mirror is called a virtual image. So you see it's not enlarged, it's not reduced, it's the same size as the object. That distance here, okay, so the distance between the mirror and the object equals to the distance between the mirror here, the surface of the mirror and the image. So when light, so you have many ray produced by the object. So you have a beam of rays. We only need two. We can trace only two. One of them you see here is bouncing off the mirror. This angle here equals to that angle here, and your brain will extend that ray here, and we'll see the B here. Okay, so that's going to be a virtual image at a virtual position. But you see that the light doesn't even reach here, doesn't go beyond the mirror, right? It's just bouncing off. So we cannot have, if you put a screen behind the mirror, you're not going to see anything, of course. So you're going to have beam of light coming in all direction, but we're going to pick up a few of the rays. So we don't need all the rays to be able to see that image here. Okay, so you have here another illustration. You see that you only need a few rays. So this is called ray tracing to trace out the virtual image. I think let's see if we have a mirror here. This is a plane mirror. You see, you only need, for example, 3 rays to be able to trace that image here. It's bouncing off, and it seems to come from this virtual position. You can have this ray. If you are asked to trace your image, you only need 2 rays. So this one will bounce off in the same direction. This one will hit the center, and then it's easy to trace the reflected angle, right? So this is the incident, and this is the reflected ray. Where they meet, that's going to be the tip of the pencil. Okay, and you can do the same thing for the eraser, but it's touching the optic axis here, so that's why you only need to do the tip. Can do penguin if you want, or star. But that's how it works. So the slide that I have here just explain you how to trace that virtual image. So it's a lot of application for that. So this is called a retroreflector, and it was placed on the moon when the astronaut went in 1969, I think. I don't know if it's in that year that they placed the retroreflector, but around them, and with a laser from the Earth, you can find the distance of moon. Okay, so because the light comes in a straight line with a laser, and it's going to be coming from in this direction, it's bouncing off in the same direction, and we know the speed of light in space. We can find out how long it takes to hear the ping, to record the ping, and so you can find the distance to the moon. Okay, so you can look it up. You know what kind of laser do they use to do that? So that's just an example. And then we get to spherical mirror, which are more interesting. So here you have a concave mirror. So you see it's like a cave, right? So it's a concave mirror. We can define its focal distance. And we're going to see that a concave mirror is actually a converging mirror. So it means it behaves like a converging lens. So it has a focal distance here, a focal point. And if you, it's a spherical mirror here, so you can extend here, make like a complete circle, and that's going to be here the radius, right? So if you take a compass, you make a circle all around, that will be the center of a circle, and that's going to be the radius. And here is the property of those mirrors. Here is that the focal length is half of the radius. So the focal point is halfway between the center of the mirror and and the center of curvature. Okay, here. So this distance here equals that distance here. A ray that is parallel, so coming very far away, coming from very far away, will bounce off. See, you have the normal. Here it's the normal perpendicular to this line here, will bounce off and try to go through the focal point. So it works exactly like a converging lens. So let me show you how it works. So this is a concave mirror. Concave mirror behaving like a converging lens. So this is called focal distance. So I can change focal distance here. Okay, I can change it. See how the shape changes. Okay, so I can take a small radius. So it will decrease the focal distance. So this is the focal distance. And if you take twice that distance here, you get the radius of that mirror. I think I had like a video. There was not a slide to show you here. You see, how do you get a spherical mirror? Imagine you take a perfect sphere, you cut out like a piece of it here, and then if you polish this side here, you get a convex mirror. If you polish the other side here, you get a concave mirror. In both cases, the radius, so it means the distance between here and the center, even though you cut out this part, you can find the distance between here and there. That's called the radius. The radius is twice the focal length. And so concave will behave like a converging lens. So the focal distance is positive. When we're going to use the equation, it's going to be the same equation that we use for the lenses. And if you have a convex mirror, the focal distance is negative. But in absolute value, I still have the same equation. Okay, I can define the radius here. That radius here will be twice the focal length. So you see that a ray that is parallel to the optic axis here is going to go to the focal point. And here a convex mirror behaves like a concave lens. So a ray that is parallel will bounce off, of course, but seems to come from the focal point here. And again, you have to make like a normal, if you make a normal line, so a line perpendicular to here, you see that angle here will be the same as this angle there. Okay, so let's go back to my simulation here. So that's a concave mirror. And what do you think? Do we get in here? Do we get real image, or is it virtual? Is it enlarged? Is it reduced? Is it what else? Virtual or real or upside down or upright? So you see, it works exactly the same way as a converging lens. You see that you get a real image. It's real image because the ray actually, when it's bouncing off, actually reaches the screen here, the image. So here you have a screen that you can place, and you will be seeing that image here. So you can place a screen. If you do an experiment in the lab, you can have a screen and you see the image here. You can see the image of this object there. So you see that when the object here is placed at a distance twice the focal distance, so 1, 2. So it's the same thing as before, right? Except that in that case, twice the focal distance equals to the radius of your mirror, right? Because it's make like a circle. So have the radius here. So this is the radius, twice the focal distance, so that's the focal distance. So if it's exactly at that position here, you're gonna see that they're gonna have exactly the same size. They have the same size. So that's how we can find the focal that's one way we have to find the focal distance of a concave mirror. And they have the same size, and of course it's upside down, it's inverted, it's real. As you move the object away, you see that the image is still real. It's still upside down, but it's getting smaller and smaller, and it's trying to get to the focal point. When your object is at infinity, so very, very far away, all those rays are going to turn to be parallel to the optic axis, and this is going to move here at the focal point. So that's why we can use that as a satellite dish. So to get the data from satellite coming from very, very far away. So all those data, maybe it's in radio waves, for example, all those data are gonna be come parallel to the optics axis, and it's gonna be focused here. Okay, it's gonna go at the focal point where you put some kind of sensor connected to a computer. You can do that with solar oven, for example. If you have like that concave mirror, at that point here, it's going to be very hot if you place it under the sun. So now if you take the object close to the focal point, boom, the image disappears. So you know that when you have a concave mirror, when the image disappears, that's when the object is placed at the focal point. And then you go inside here the focal distance, and the image becomes virtual, enlarged, and upright. Okay, so it means the ray don't reach the image here. So you get an enlarged image, which is virtual. Okay, so it works exactly like a converging lens. I think I have posted a video here.
So hi guys, so what I have.
So let's remove the sound. I have posted it, so it's posted already. So I have like here, I have
Here is a mirror for makeup. So it's a parabolic.
So a typical concave mirror is a mirror for makeup. This is my object, And now you see that you have an upright image, enlarged, and virtual. That means the image is beyond the mirror. That means the distance between the mirror and the object is smaller than the focal distance. And I'm going to move the mirror away. So it's still enlarged. So I'm going to move it away. And when the image is going to disappear before it's reappearing again, that means it's at the focal focal distance. So you see, moving away, see moving away, and that now the image here disappear. That's going to be the focal distance of the mirror, and then it's going to reappear again. It's reappearing again, but now it's going to be upside down. Here, it's going to be upside down, and in that case, it's going to be a real image. That means it's an image that you could see. If you put a screen here, you will be able to see that image here. So it's a real image, it's upside down, and if it's the same size, that means I am at the distance equals to the radius, and then as I'm moving further and further away, I get a smaller and smaller and smaller image, which is real. And close again, proof it's upright again. So that's how those mirrors work. You can play yourself with it. You get a makeup mirror, they are very cheap. And see, as you move away, you get a smaller image. As you move closer, boom, it disappears, and you get an enlarged image. So this is enlarged, virtual, upright, and here you have a real image but inverted. When it's the same size, that means the distance here is twice the focal distance. Okay, so I hope everything is clear. So for ray tracing, you only need two rays. So the one ray that is parallel to the optic axis will bounce off the mirror and go through the focal point. The ray that is going through the focal point will bounce off and be parallel to the optic axis. And the ray that, for example, wants to go through the center here, and this is the radius here, will bounce off and will not be deflected. So you have three rays, but you need only two to trace your image. So here, for example, you have your object here, and it's between the focal distance and twice the object, twice the focal distance, the radius. So it's in between the focal point and the center. So you get a real image. That means you can place a screen here. You will be able to see it. It's going to be inverted and it's going to be enlarged. Okay? Now, if you place your object farther away, it's still going to be inverted, but now it's going to be reduced. When you place it here, it disappears and reappear here beyond the mirror. So you have to play with it. Example application, you can make a solar power plant. So you have a mirror here, and if you follow a line, it makes like a parabola. Okay, so you follow that parabolic line here, and all those mirrors on that line here, they're gonna send the light from the sun, so the light comes parallel. I mean, all parallel, not necessarily straight down, but all the rays come parallel, and all those rays are gonna be focusing here. That will be the focal point of all those mirrors here. That will be the focal point here. at that focal point here, they have like a oil container. So they are boiling the oil that will create somehow steam that will turn an engine to produce electricity. So you have a lot of applications for that, like here. I think this is experimental, but it's the same idea. You have a dish, and you might ask, how come it's not spherical? How come now we are talking about a parabola? I will explain that later. But it works the same. All the rays that come parallel here will be bouncing off the mirror and be here. Come here at the focal point. So any ray parallel to the axis here will bounce off and hit that point here, which is called the focal point. Now you have also virtual image. I don't know if I should do first an example. Let's do the real image first. So let's do that example here first. You can pause the video and try to do this problem. So 2 centimeter high object. So I'm going to call that H. That's your object. Is placed from a concave mirror. So I know it's going to behave like a converging lens. So that's going to be G sub I. The radius of curvature is 10.20. So the radius is 10.20 centimeter. So they want to find D sub I, so D sub O, this is the object, and the size. So this is the radius. That means that the focal length is positive because it's concave, and it's going to be half of that, so 5.1 centimeters. So let's see, you have your mirror here. So you have the focal point here, you have your C, the center, to make like a sphere. If you make a sphere, a circle, that will be the radius here. So this distance here is twice that distance there. And so that distance here is what? That's 10, so 10.2. And your object is inside. So we expect to have enlarged image upside down and real. So this is 5. So maybe it's here. So you know that one ray that is parallel here will go through the focal point. A ray that goes through the center here will not be, it's going to go back in the same direction. So where they meet here, it's going to be here. It's going to be your image. That's your image. That's your object. So it's a real object. It's upside down. And it should be enlarged. Okay, so let's see. Use the same equation. So 1 over 7.1 plus 1 over the image equals 1 over 5.1. So we already saw how to solve for those. So you have 5.1 to the minus 1 minus 7.1 to the minus 1, enter, and to the minus 1, enter, and you get 18.1. So that distance here is going to be 18.1 centimeter. That book comes, this problem comes from Cutnell and Johnson. That I recommend for the MCAT. And then what is the magnification is still minus d sub I over d sub O. So it's going to be minus 18.1 over 7.1. And you get minus 2.5. So the size of the object equals minus 2.5 times 2. So it's going to be minus 5 centimeter. So it's not really on scale, but if this is 2 centimeters, so it's about that, right? 1, so this is 2, and this is 2, and this is 1. So the size here is going to be 5, or minus 5. So virtual image you get when your object is inside the focal distance. So its virtual image is going to be enlarged. So how to trace it? So you take a ray. You have, so that the ray, for example, that wants to go through the center here, it's going to bounce off and comes in the same direction. A ray that wants to be parallel, it wants to go through the focal point. And this ray here that seems to come from the focal point wants to be parallel. So you have 3 rays like before, except that now they meet, instead of meeting in this side here, is they are meeting on that side. So we're going to see that the distance to the image is going to be negative. So the virtual image is here, and it's going to be enlarged. It's going to be erect or upright, and it's going to be virtual. So applications, makeup. Other example is interesting technology. Here you have virtual image on the windshield. It's going to tell you, how far the car in front of you is, or it's going to tell you your speed or other information. And the way it works is that here you have the object, which is the screen with the numbers. And you see the beam here is going to bounce off a concave mirror, and then it's going to bouncing off a plane mirror, and what you see is a virtual image beyond that mirror here. So it's like a setup with 2 mirrors. So first you get a virtual image because of the concave mirror. That virtual image becomes an object for the plane mirror, and you have the final image here. So you go from object here, image 1. Image 1 becomes object 2. Object 2, you get a image 2. If you follow the beam, it makes sense. It seems to come from here. That's a nice application. So you are using exactly the same equations. So let's try to do this one. It's a virtual image by a concave mirror. So it's like a magnifying glass. So it works like a magnifying glass because it works like a converging lens. So you have a virtual image is when you have it's like a magnifying. It's magnifying. So you have your optic axis here, and now you have your mirror. Okay, you still have your focal point here, you have your C here, and now it says, what does it say? 6 centimeters, so that's going to be D sub O. And the focal distance here is 10, so that means this distance here is 10. So that's F equals plus, because it's concave, 10 centimeter. So you want to find the location of the image D sub I. And the height is 1.2. So now the object is inside the focal length, inside the focal distance. So this is 10, somewhere here. So you only need 2 rays. So one ray that is parallel here wants to go through the focal distance, and a ray that goes through that point here. So it bounces off in the same direction. So now you see how the rays are diverging, and they're gonna meet here somewhere beyond the mirror. So it means inside the mirror on that side here. So you have a enlarged, it's upright, and it's virtual. And from that side, you see that the rays are diverging. So if you use the same equation, you're going to have 1 over 6 plus 1 over d sub I equals 1 over 10. Okay. So d sub I equals minus, and you expect, so minus means it's virtual. Okay, so this is not bad, right? This is a 15. This is 10, this is 15, okay? So this is 10, kind of, it's not very on scale, but not bad, 10 centimeter, 15 centimeter. Now the magnification, it's going to be minus d sub I over d sub O. So it's going to minus 15. D sub O is going to be 10. So it's going to be 1.5. Not 10. D sub O is 6. It's going to be 2.5. So it's positive. Okay, it's going to be 15 divided by 6. Right, it's going to be 2.5. So it means y prime equals 2.5 times 1.2, which is 3 centimeters. So this is 1.2, which is 3. Okay. Now, we have an issue with when we make those mirrors. So for makeup mirror, doesn't matter. But if you want to make a larger mirror, or if you want to use a mirror for a telescope, that's not going to work very well if it's a spherical shape, because it works for rays close to the optical axis, but for the ray farther away, they are not going to go through the focal point here. So this is called spherical aberration, and it's an issue for telescope. Okay, so we don't make spherical mirror. Actually, we make parabolic mirror, such as all those rays here that are parallel. They do focus here at the focal point. So a telescope will have actually a parabolic mirror. Okay, so we can deal with, it's called spherical aberration. So for example, that was an issue with the Hubble telescope. It was not nicely, it didn't have a nice parabolic mirror, so they had to go in space, and luckily they were able to fix it, and you see the difference, right? It gets fuzzy when the ray don't focus at the focal point. especially when you have a telescope, you are looking something very far away. So all the rays come parallel and should focus here at that focal point. The image will be here, and then it's connected to a computer, and then it's sending information to Earth. So in a telescope, we make parabolic mirror. So that's how a telescope works. You have rays coming from very far away. It's going to bounce off that mirror here, concave mirror, and wants to focus at the focal point. And then you have a plane mirror that brings the focal point here. So you have the image of your galaxy at that point here. You put your eyes here. This is just a magnifying glass to make it bigger. So that's how it works. You don't want to put your head here on the way, because then you're gonna get a dimmer image. Okay, so that's why it's you put your eye here on the side and not here. You don't want to put your head here. So the first telescope, the reflective telescope, was designed by Isaac Newton. That's a copy of it, 1660. Okay, so then we go to convex mirror. So convex mirror, they are used in surveillance or blind intersection. So they work like a concave lens. So that means you always get a virtual image upright and smaller. So the focal distance is negative, and then the distance to the image is negative as well. So if I go to my simulation here, what you have here is convex. It's convex mirror behaving like a concave lens, so it's a diverging mirror. So if it's very, very far away, the image will be seen here at the focal point, and then if I come closer, you see it's still smaller, it's still virtual, it's still upright, but it's always virtual. Virtual, all the way virtual, all the way upright, all the way smaller. So it behaves like a diverging lens. Something happens. So here I have a demo.
This is a convex mirror.
That's what it looks like. You can find his he has a YouTube channel with a lot of demos. It's called Demos Physics.
Bulging out
So you have
toward us.
so this is
And I'll be doing the
convex.
same experiment we did
Here
with
he
the
has
convex
two
mirror.
markers
And,
here. That
it's a
will be for the
concave mirror, that
focal
is.
distance.
And I'll be backing
That's
away
going to
from
be
it
for
and
the
looking at what the
radius.
image
So the
does.
radius is
So
twice the focal distance.
My nose up against the mirror.
See,
It's an
still
upright,
gets smaller image.
virtual
It's
image.
virtual, it's beyond. And as he moves away from the image, you're going to get smaller and smaller and smaller, but it's still virtual.
Image. So the radius is
And it's
shorter,
very,
still upright,
very useful
virtual,
in blind intersection, for example. And they will put a sign. What you see in the mirror seems
than the concave mirror.
things can appear closer, farther away than they are really, they really are. See. So here, if you look in the mirror, you see the things that is very close. It's the opposite. Okay, so if you look in the mirror here, you see it seems very close. If you are looking for it, when the object is very far away, then we get see how it works here. Okay. So the object can no. The saying is that the object can be closer than they appear to be. Okay, so here to trace, you see the image here is upright and it's smaller, so and virtual. So image here. So what you do to trace, to do ray tracing, you need only two rays again, but that's going to be this focal point that's going to be involved here. So a parallel ray will be bouncing off like it's coming from that focal point here. And then a ray that seems to go to the center here is bouncing off in the same direction, but you can extend that ray here. A ray that is wants to go to the focal point here, doesn't reach it, it's going to be bouncing off and it's parallel. Okay? So that's how you do ray tracing. You only involve those 2 points here, that focal point here and that center here. So that's just a summary. So for a virtual image, d sub I is negative. For a concave mirror, so converging mirror, f is positive. For a diverging mirror, f is negative. It's also called a convex mirror. Okay, so let's try to do this one. A few more problems and a few more. I'm going to show a few applications. Okay, so let's see. So it's a convex mirror. So here you have the optic axis. Not great. So you have a convex mirror here. And what matters? Matters is the focal point here and the center here. Those 2 points, they are the one I want to make the ray tracing. Okay, so 66 centimeters. So it's very far away. Okay, so you have an object here, and that's going to be D sub O, and it's very far away. Okay, so that distance here is 66 centimeters. Comes from very far away. The focal length is 46, so it's going to be negative 46 centimeters. So that's going to be here 46. So it's far away, so it's going to be, let's see what's going to happen. So let's make one ray. So we know that one ray, the ray that is parallel to the axis, wants to go here. So it wants to go there, but actually it's bouncing off here. So it's like diverging away. And the ray that wants to go to here, I'm going to make that. So the ray that wants to go here, it's going to bounce off in the same direction. So where are they going to meet here? They're going to meet somewhere there. So it's going to be a virtual image very close to the focal point. So I'm far away. And you see that the image is always inside your focal distance here. So this is 46. That's going to be about here. I'm going to be there. So it's going to be upright. It's going to be virtual. And it's going to be virtual and upright and reduced. Okay, so I'm going to use the equation. I'm going to have 1 over 66 plus 1 over d sub I equals minus, don't forget the minus, 1 over 46. And you solve for d sub I. We did that together. a lot, so I'm just giving you, of course, you can pause the video. You should always pause the video. Make sure you get it right. So minus 27 centimeter. So this is, here you have 27. Okay, it's not bad. Drawing, not a bad drawing. Okay, so the magnification is going to be minus d sub I over d sub O. So it's going to be minus, and here you have minus 27 over 66. So it's smaller than 1. So that means I get a smaller image. And okay, so that's going to be the magnification. The radius R, it's going to be 46 times 2. That's all. So if you see here, if I make like a circle, the radius here is going to be 46 times 2. Or 46 times 2. Okay. So this one is, it's a nice drawing, because you see, when you have a plane mirror, you expect to have a virtual image here. But you can see that when you curve that mirror here, it's going to bring back the image here closer. Let's try to do this one. So that's going to be d sub O equals 9 centimeters. So if it was a plane mirror, and so let's say you have your image, you have your object here, the distance is 9 centimeters. If it was a plane mirror, then the image will be here. Okay, that will be 9 centimeters. That's for a plane mirror. But because I have a convex mirror, so it means something like this. Now the image is 3 centimeters closer. So that means the image here is here. So that means d sub I equals minus, it has to be a minus because it's virtual. So that's virtual image. And d sub O equals 9 centimeters. Okay, so you have 1 over 9 minus 9 over, no, it's 6 centimeters here. So 1 over 6, because it's 3 centimeters closer. So that's 3. So 9 minus 3 is 6. That's going to be 1 over the focal line. Okay, you have the picture here. So 3 centimeters closer, it's going to be 6. Okay, so you can do the math. It's going to be 9 to the minus 1 minus 6 to the minus 1. Okay, to the minus. Okay, so that's going to be minus 18 centimeters. So the only thing here was to understand that the image for a plane mirror is at the same distance. So that's going to be 9. 3 centimeters closer, that means that's going to be 6. Okay. That's a solution for this one. Okay, so here you have an interesting application, and that's called the keratometers. Is to measure your pupil. Your pupil is like a convex mirror, and I'm sure you have been to the optician. You look through it and you see a little image like an airplane. Sometimes it's a hot balloon that you are looking at. Okay, so you are looking at that hot balloon here in the mirror, and then the optician is going to see a virtual image because the light, I mean the object here, the light from the object, it's going to bounce off, and the optician here is going to see a virtual image form beyond your pupil. So it means you are using your pupil here like a convex mirror. Okay. So you can pause the video. I'm sure you have seen those with a mirror. It's called see, that's what you see here. And so that will be the object, and the optician is going to see that virtual image form beyond your pupil. Okay, so it means that it's called the mirror. I don't know why they very often they use a house or a balloon, so it's easy to see, the size. So you have this is the optic axis, so that's your eyes. So that's your eye. Okay, that's you here. That's your nose. So that's your eye here. And somewhere here you have an object. And you want to find the radius. So remember what matters. You have the focal point here and you have C. So they want to find that distance here. So that distance here, R equals twice the focal length. So that's your eyes. That's your eye. So you're going to get a virtual image smaller than the object. Okay, the object is placed 9 centimeters in front of the cornea. So you have an object here, okay, which is 9 centimeters. So that distance here is 9 centimeters. And of course, you're going to have a ray that is parallel here, wants to go for the focal length, and a ray that wants to go for here. It's not going to be it's not going to be it's going to go in the same direction, right? So the image is always formed somewhere here, and it's going to be upright. So somewhere here I'm going to have like a virtual image. Okay, so that's going to be G sub I, and that's going to be G sub O, and they want to find R. So to find R, I need to find the focal distance. So what do we have? We have that, we have something else. The magnification. Yes, because they look at, this is the balloon here. And the optician is located here. He's looking and he's seeing that balloon here smaller. So he can find the size of that balloon relative to this one. So the magnification equals to, it's not on scale, okay, obviously, this is I, 0.046, which is equals to minus di over d sub 0. So from here, and we want to find f. So, and we have d sub 0, okay, so we have 0.046 equals minus d sub 0 over 9. Okay, so we can solve for di. So di equals minus 0.046 times 9. So di equals minus 0. You have to do it to make sure I didn't do mistake. 0.414 centimeters. So that's going to be d sub I. So it's somewhere inside the eye here, inside the focal distance. That's going to be d sub I. So then you use the equation 1 over d sub O is 9 plus minus 1 over 0.414 equals 1 over the focal length. So you do this. This is just simple algebra, and you get minus 0.43 centimeters. So to find the radius, you multiply this by 2 in magnitude, and you get 0.87. Okay, so that's interesting problem. Also comes from Johnson and Cutnell. So the idea is that that's going to be your eye here, and the optician is here, and there is a object which is a balloon. Usually it's called a mirror, and the optician is going to see the image of the balloon beyond your pupil, and by measuring this distance here, measuring the magnification, you can figure out the focal distance. If you have the focal distance, you have the radius of your eye. So that's cool. So here it doesn't give information if the mirror is convex or concave. But here it says it's twice, so it's enlarged. So if it's enlarged, it has to be concave because it's like a magnifying glass, right? So it's converging. It's a converging lens, so it has to be concave. Okay, because with a convex one, you cannot get something enlarged. It's only with a concave one that you can get enlarged. Okay, so now we know it's a concave mirror. It has to be concave mirror. So we know the radius, which is 24 centimeters. And we know it's a concave mirror, which means that the focal distance is positive. So the focal distance has to be equals to positive 12 centimeters. So we have the focal distance. And the image is twice the size of the ring. So that means the magnification is 2. So plus 2 equals d sub minus d sub I over d sub O. But they don't give you, do they give you the distance? So you have to figure this out, right? So we have 2 equals minus d sub I over d sub O. And we have 1 over d sub O plus 1 over d sub I equals 1 over 12. So you have 2 equations with 2 unknowns, but what do they want? They want d sub I, no, d sub O. They want d sub O. So you can pause the video. So I'm going to use this equation here. I'm going to get rid of d sub I. So d sub I equals minus 2d sub O. And I'm going to plug that into here. So it's going to be 1 over d sub O minus 1 over 2d sub O equals 1 over 12. We put that at the same denominator, so it's going to be 2 over 2d sub 0 minus 1 over 2d sub 0 equals 1 over 12. So you have 2 minus 1. So that's going to be, you have 1 over 2d sub O equals 1 over 12. So you compare this one and that one, then d sub O equals 6 centimeters. Okay. I think there is a last one. So here we have an object that is smaller. So it has to be a convex mirror. Has to be a convex mirror. So that means d sub I is going to be negative. It's smaller, okay? The only way you can have smaller virtual image is that you have a convex one. You see, it's virtual. So that's why you have to play with those simulations. Very helpful. So that means here, that means that's d sub O. So this is d sub I, but it's smaller. It's virtual and it's smaller. So the only way it's a convex mirror. So since it's convex, that means d sub I equals minus 4.5 centimeter. D sub O equals 7 centimeter. So you're going to have 1 over 7 minus 1, 4.5 equals 1 over F. And you get, if you do the computation, minus 12.6 centimeter. Okay, let's review this one. The image is twice the size of the ring. Okay, so it's enlarged. Okay, so that was correct. I think this is correct. I will check this out, but I think this is correct. And this one is correct as well. Minus 12.6. Okay, so let's go back to here. Okay, so now it's going to be all conceptual question that you can get. So just a parenthesis here. You see how those concave mirror can be used? These are satellite dish, so rays coming parallel from the satellite. So you have to orient the dish the right way. All the rays gonna be focusing here. This is called a feed horn. So it's like a sensor. It's gonna collect the data and then it's gonna be sent to a TV or whatever it's used for. But interestingly, you don't need the whole dish, okay? You just need part of the dish. You don't need to collect that many rays. A few of them is enough because each one of them carries exactly the same information. It's just a problem if you are looking in the optical light, then you want the image to be as bright as possible, so you need to collect as many beams as possible. But in that case, you are collecting radio waves, so you don't need the whole dish. And that's why here you have the feed here at that location there. Lots of applications here. That's when in the 60s, they were trying to find a good number for the AU, the astronomical unit, which is the distance between the Earth and the Sun. And for that, they found the distance between the Earth and Venus. So they will send a signal, a radio wave signal that will bounce off. Okay, so it's like a radar bouncing off here. So they knew the time it took for I think it's microwave to bounce off Venus, and they knew the speed of light, so they could find the distance. So it has a lot of applications. So here, for example, you can use to find the speed of rotation of Mercury. So you bounce off that light here, so it's bouncing off and it's coming back. So it's like there was a reflection here. And if it's spinning at the same time, here it's going to be, you can find that rotational speed, because there will be a change in the frequency. So in that case, the frequency is going to increase. In this case, the frequency is going to decrease. So it's the Doppler effect. But that's another topic. Here you have, you can use those dishes to make a radio telescope. So you have all those dishes, you connect them together, you get a network of dishes, and the size of the network, everything happens like you have a huge radio wave telescope, the same size as a network that of all those dishes connected to each other. So you see they are looking in the same direction. So you have all those radio waves coming from space, from a galaxy or a black hole, and all the rays. This is a concave mirror, so all the radio wave will be bouncing and come to the focus here, because a ray that is parallel will bounce and it's going here at the focus of the dish. how they used to make them. So they don't make them like this now. They have small dishes connected to each other, and it works. Everything works like it is a huge dish. So this is broken. It's a very famous telescope in Puerto Rico. It's called the Arecibo telescope, but same idea. Rays coming parallel to each other will be collected here at that position here, which is a focal point. And you have to look it up because the Arecibo telescope was the one that was able to detect the first exoplanet. And it was featured in a James Bond, there's a typo, James Bond movie, it's called The Golden Eye. So reflection of light, lots of applications. So for example, if you have a radar, you send light that will bounce off an airplane. So you know the speed of light, you know the time. It's like echo. It's like an echo, right? It's a light echo. The time it takes to come back, and you can find the distance, and you can find the location of the airplane. So this is a radar, and it's using microwave. We see the beams here comes parallel. It's going to be focused here at that focal point there. And of course, that's a problem in the military. Maybe the enemy doesn't want to be seen. So that's why they have developed something called the stealth technology. So when there is a microwave signal, the signal does not come back in the same direction. Instead, it's going to bounce back in the other direction. So now it's invisible. So that radar technology that relies on reflection was developed in World War II by the British. And it's advanced technology. And then the technology was, after the war, was brought in the US and other part of the world. And it took the American a while before understanding how it works. Okay, it's a very nice technology. So it's called the radar. It's used what it's called a magnetron, and it's the same technology that we use in the to make those microwaves. In a microwave. Microwave use the same technology that we use in a radar. So anyway, that's a tangent. So you use those stealth technology to design airplane that cannot be seen by your radar, because light, instead of bouncing off in the same direction, it's going to bounce off in another direction. You also have stealth technology for submarine. So the idea is to make very sharp corners here, so light will tend to bounce off in another direction. Okay. Here you also have reflection from the layers in the atmosphere. So during the day, you see the layers move, day, and then that's going to be night. See how it's bouncing off? The broadcast, if you are broadcasting something, it's going to bounce off, and then you can listen to the broadcast farther away here. So at night, it's easier to pick up the AM signal. So only AM radio waves, so with a smaller frequency. Is it smaller frequency than FM radio? Smaller frequency than FM radio? These radio waves will bounce off the atmosphere, so you can listen to the radio at a larger distance, especially at night, you see. Another application that I found nice, I think it's a student of mine that sent me this. You can use like when we do not have electricity, you have a water bottle here. At least this is a nice use for this bottle. and you see that the light from the sun is going to enter the bottle here. It's going to bounce off. It's going to have a total reflection, and finally it's going to escape. So it makes like a lot of light inside. So also reflection. So light is not the only wave can be reflected and used in technology. You have also reflection of sound waves. So in the domain of seismology, for example, you can have an earthquake or explosion, and you see that the sound wave will be reflected off different layers inside the earth. So it can be refraction here, or you can have reflection. By using those seismic waves, you can see the inside of the earth. So this is called tomography. So this is called tomography. And so seismology. So you can see the inside of the earth here. You see what's going on inside. So it's all using also reflection. With reflections, you see it's called seismic reflections. So you send seismic wave. So you send a sound wave that will bounce off the bottom of the ocean, and you can probe the inside, for example, the outer layer. Maybe you are looking for petroleum, and you can also find the distance. So you can kind of scan, and you can scan the bottom of the ocean to know what it looks like, to get an image of it. Echo, it's also like a wave bouncing off. And of course, you can find the distance if you know the speed. The speed of the sound is about 1 mile in 5 seconds, about 340 meters per second. So you can use sound waves, you can use echolocation to find the depth of the oceanic floor. That's echolocation again. You can use these equations here. So if you have the speed, you have the time it takes to bounce off, so you have the distance. And of course, it's used by animals, right? It's the baleen, the whale here. It's gonna produce a sound wave that will bounce off, and that way the whale can locate the krills or maybe the fish. It has a lot of application also with a camera. So it's autofocus. A lot of application. You can get also, instead of probing the earth, getting a 3D image tomography, you can use it also with ultrasound. And of course you have the image here of the baby. It also has to do with reflection. So we are using ultrasound, but it's still sound, right? It's just sound that we cannot hear it. Interestingly, this is in Belfast. If the way it's because it has a nice elliptical shape, if you whisper here, you can hear the sound there. You see, if you have an imaginary line, it's a normal line here. You have that angle here will be equal to this angle here. It's going to bounce off nicely. It's called a whispering chamber. You have the same thing here in New York City, in Grand Central. So you stand in one corner and you can hear it at any corner around. Reflection can happen also with strength. You see, you make like a pulse. It's gonna